All right, everybody. We're back again for another episode of the Future of Data. I'm your host, Omar Alngar, and
I'm Jan.
today, we're gonna have a great conversation about lineage and self-sovereignty. Now, I believe in our last chat, we ended up finishing on this concept of diving really deeply into data and computational lineage. But I think it's important to sort of really drill into how this applies in a world where everything is not just done by default on the blockchain. So I'm actually going to go and dip into this concept of self-sovereignty a little bit before we touch on the lineage pieces. And in particular, I'll talk about, let's say the dangers of losing firewalls, especially in the context of, common Web3 solutions like IPFS and public Web3. Then we'll come back here and get into the meat of it with data lineage. I can go and show you guys how we did this in a sample for medical data for training an AI model. And then for computational lineage, Jenny, maybe you can show us one of the more fancy ones that we've done for, let's say, showing a full lineage of Fibonacci proofs, I think calculations, and even some of our API lineage. And then for, a lot of this was actually in the context of how are we going to go and show when an AI model has used specific bits of data in training. And we talked about some of the articles that have come out just this week about the EU AI Act, where they're trying to go and provide guidelines for how companies need to report training models. Let's say guidance on foundational model training, as well as fears over training on copyrighted materials and personal data. And maybe we can wrap up just by talking a little bit about, why this is important in the context of firewalls and an example with our customer Genobank. What do you think, Johnny? Anything else that you add to our list for today?
No, I think it's enough for
Yeah, it looks pretty good.
half an hour.
No, I think we're even a little late today. We might only get 25 minutes. Well, let's start again with this idea of self-sovereignty. Maybe you can actually tell a little story about this. Let me see if I can update a few slides in our deck over here with some of my more recent pipe dreams. Just a second. I will pause my work to show how the sausage is made. And I'll note that one of our things at WeaveChain is really emphasizing that we are a self-sovereign Web3 data solution, as opposed to traditional public and permissionless solutions like IPFS and Arweave that really claim to be self-sovereign but are not quite. So let's go ahead and start with how we actually got here and the origin of WeaveChain, which was in another project that we worked on, Johnny, our beloved Mono.ai. Let me see here. Resume the share. So, we've been on this mission to go and see if we could build a product to automatically quantify all time. So I've been running a project where I've tracked my entire life for about 6 years now. The data is fascinating, but what we try to do with Mono is see if we could actually go and do that automatically and use pretty much every bit of your digital footprint and artificial intelligence to go and figure out how you spend all your time and help you spend time better. It was going great, but unfortunately, we ended up building the world's greatest spyware because we just had like really, really sensitive information about users. All this integration data of what you're doing on your computer was stored on our SaaS web server. And the trick here is that, if this is storing everything that I do for work, even if I go and summarize that data and don't have the hyper-specific what I was doing at 1140 AM bits, this still has sensitive information like what customers are being worked on that need to be managed at an enterprise grade. So as we were building this, we got really excited about Web3 technology because it seemed like the perfect solution where everybody talks about how in Web3 users will own their own data and have this record of every time that it's used, including whether it was used in training the AI that we were using for our product itself. we also got really excited about using token rewards and using confidential computing to preserve individual privacy. As you know, I am a big proponent of Web3 data concepts, but the problem is just that like 99% of data can never exist on public Web3. So this vision of Web3 being, ownership of data, there's a catch. There's always a catch in the case of public Web3. It's that you have to go and completely abandon firewalls if you're going to use any of these services and basically only use today's encryption for safety. So, all of these public Web3 data solutions over here, the spoiler alert is that they don't comply with global regulations, that they never will. We talked last time about the inability to delete data for GDPR and CCPA compliance. But I'll note that, the trick with something like public IPFS is that if you're going to go and put data there, the content ID itself is actually a hash of the data, because the data itself, like, let's say there's a tight correlation between how you're going to reference it and that CID. And if somebody was able to go and, let's say, access your data using that CID and have that encrypted copy on their server, if they were able to break your encryption, either by getting your private key or with quantum computing, then suddenly your data is available in the public forever. And I'm of the opinion that there are entities out there that are scraping public Web3 and just storing all that information in the case that happens. Now, our pattern with WeaveChain is a little bit different, right? We've gone for a layer 0 pattern where we don't believe that people are going to go and do full decentralization all the time. We think that it needs to be a little bit more deliberate. So our product says keep your on-prem computation and database processes, leverage a WeaveChain node on-prem or like on your mobile phone for an app, and then build these private dApps where you're sharing data selectively with whoever needs it and whoever you permission to do so. The layer 0 pattern means that we're going to have a lot of sidechains for this. And then we go and establish Web3 security by putting just anchors on any layer 1, so that these anchors, can maintain GDPR HIPAA compliance because they don't have any data in them, but still have that cool security pattern. We also deal with bridge tokens, and we can do this for any layer 1 or layer 2. But again, when I think of self-sovereignty, to me, it's this idea that I will be the one that holds my data on my device, and I will give it access to other parties for that data deliberately when it's appropriate. And then I'll still be able to benefit from all these nice things like, anchors and tokens.
I would mention here that it's actually a gradual shift from self-sovereignty to have a data broker and to have a public network that keeps the data. We try to accommodate all the information, all the species, meaning that you could have a public sidechain that acts just like IPFS, or you could have a public sidechain that is a data broker and delivers data on behalf of other users.
Oh, beautifully said. I mean, I let's say pick on IPFS a little bit in these scenarios for compliance reasons, but there's a lot of good reasons why you would go and use IPFS as a storage mechanism, or let's say have a public sidechain that has the data available, for anybody. And it's particularly good for these public good scenarios where you want the whole world to have access to this data in a free capacity. And when you're doing so, we do believe that, these sidechains can go and achieve the same result over here. That said, this is not what I want for my personal data, right? Like my healthcare data or my personal credit card information or financial data, or even like my personal documents where I write my notes. I do not want that in an environment that doesn't have firewalls. I think, it's sort of, I can't remember if we brought it up in this context. Let me see if I can go and fish out my slide for it. But if you're going to go and try to protect your data, I think that, there are a few different features that you want to go and give it. Let me see if I can put this over here really quickly. So if I am trying to go and lock down a database at enterprise grade security levels, the first thing I'm going to do is set up that firewall so that nobody can get even close to that data unless they are a permission party. Then if somebody's inside the network, I'm still going to make it so they need a special username and password to get access to specific rows of this table. I'm going to encrypt the data when it's at rest to make sure that if somebody actually gets hard coded access to the database, they can't decrypt it. I'm going to encrypt the data when it's in transit. And then I want to go and add immutability guarantees to this data set. And ideally, like, utilize a trust network to have a distributed defense so that, even if one environment's breached, not all four are. The idea that I'm going to go and get rid of firewalls in this scenario, though, is crazy to me, right? Like, the US government went and issued an executive order in 2021 saying that they wanted to go and protect their logs with cryptographic methods, just like we've been describing, but they are absolutely not getting rid of their firewalls, right? And like, US government firewalls are one of the key protections that they have to make sure that nobody can go inside their network and be monkeying around. So really, we're pursuing a solution that gives us a sweet spot for getting all these things all at once. Now, I mentioned earlier, this is all in context of how we're going to go and establish a lineage for data, because this does complicate life a little bit. In a public Web3 environment, one of the nice things is that everything that you do on the blockchain is visible to everybody at all times. So every execution of a smart contract is represented in a block that anybody can see and verify that it happens. So the question is, what do we do in a scenario where we can't go and have that block explorer having all that sensitive information, and instead the blockchain only has, let's say, these anchors that have really no meaningful data in them besides a guarantee that the data hasn't been tampered with? This is where we go back to frankly, legacy forms of cryptography. So I'll go through this one vignette over here. Let's say that we have a hospital that has my medical data on it. Weavechain makes it very easy to go and read data from the server for things that are not sensitive, like a directory of different hospitals in the network. And as noted, our blockchain anchors are basically these hashes that are generated from bundles of data. So here you see hashes that are created from ID, 1 to 1,000, 1,001 to 2,000, etc. And these are the kind of things that we can go and put inside of a smart contract to go and guarantee that this data has never been tampered with.
So this is one of the possible immutability proofs. So the hash is for batches of data. There are others, which we discussed in a previous video, I guess.
You got it. Now, important to this scenario is that we do not want to allow a researcher, for example, to go and see my personal patient data, right? Like, I don't want them to know, when my last colonoscopy was or whatever it is. That's my private information. What we do want to enable, though, is for the researcher to be able to go and run studies on the data and get results, like understanding the correlation between smoking and severity of cancer, without seeing my personal information. And this can be achieved with confidential computing techniques, which I'm sure we will go over in another call. But it is one of the sort of key features that we see of modern Web3 data approaches. So this first algorithm that I ran over here is a multi-party computing algorithm, where you're applying a relatively simple algorithm to a variety of variables. So in this case, we're doing a correlation. Go ahead, John.
Actually, we did a degenerated form of it because we used a single node in this case, but
yeah, we can do it for
any number of nodes.
You got it. Now, of those different forms of confidential computing, another one is compute to data, where I can run any arbitrary code on a remote data set, as long as I have permissions to do so. So in this case, I have some Python code that's going to go and train a machine learning model on all of the patient data that's available to us. And what happens in this compute to data scenario is that we actually have a Docker container that's running Weavechain as well as this Jupyter notebook. And when I execute this compute to data task, we're going to go and spin up another Docker image that's running this computation through the Weavechain node and can return to us a trained machine learning model without us ever having seen the data itself. What's cool about this model is that it lets us go and show, the correlation between alcohol usage and cancer severity, again, without having ever seen an individual patient's data. now we get back to the lineage part of things. Unless Johnny, did you want to add anything?
No. I mean, maybe mention that the Docker images can be restricted. So both in terms of what's the output that you can retrieve, but also on the security side, they can be restricted to not be able to use the network and other stuff like that. And yeah, you can run literally any code with Docker images. We also support WebAssembly, which is a bit more restrictive. It's a different way of compute to data. But
No,
yeah,
it was a great call out. I actually like to use slides from Baka Yao to talk through, let's say, how these confidential computing scenarios need to go. So they made a really cool little vignette that says, let's say that I have some really sensitive data that org B wants to go and get access to, but org A has to go and deal with regulations and make sure that they're not exfiltrating the data for. In a really nice scenario, when org B asks for access to data, the holder of the sensitive information should actually go and look at the code that's being run to go and make sure that nothing is being blatantly exfiltrated. Then they could go and let that code run on their servers and then generate some results. And even those results should actually be audited by the data holder to ensure that no sensitive data has been exfiltrated in this scenario as well. And then they can return to org B and everybody's happy. What Johnny was mentioning earlier is that, in this step, we can actually audit programmatically and say we will not let data of a certain size threshold leave the network or data that has certain pattern matches in it. And even like at this point in time, when the data holder is accepting the job from the researcher, they can go and whitelist a few jobs that they have, let's say, audited in advance to make sure that the researcher is not running arbitrary code in this environment. A small digression on the challenges of confidential computing, but let's say that we are comfortable with the code being run here. How do we go and establish a lineage to show that computation has run on specific data and produce a specific result? What we do at WeaveChain is say, let's go and take hashes of every piece of this process here and say, I'm going to go and take a hash of all the data that was used for that to train that algorithm. I'm going to take a hash of the Docker image that ran, the code that trained the machine learning model. I'm going to take a hash of the output, and I'm going to sign it all by the node that did the calculation. And what's really nice about this scenario is that if you do have a nice trust network of multiple parties that are collaborating over here, each one of these parties should, in theory, run the same calculation against data that it has access to and get the same result, but sign it independently. And you almost create computational reproducibility by default with your data. Johnny, maybe you could walk us through another more discrete example over here, but with a sort of simpler calculation.
So first, if you go back to the previous notebook, so what we did here, the input hash is actually a hash of the hashes of all the data that enters the calculation. We track a table level. So whenever you do some read operations inside the Docker, those are audited and the hash of the data is correct. And then
you're talking about these calls right here in the code, right?
Yeah, for example, yeah. But just as well, we can track the reads and also if you get some data from internet or so that's the input hash. And the output hash, we have two types of outputs. One is the result that it's produced by the task. So let's say a generic blob that is a result, but it can be also writes in the tables because our node supports access to any database. Also, the writes have a separate. They are not in this sample, but any operation that so any output, any write in a table also is tracked the same way as here. So we have the input, the compute hash, and then we have a hash of the output. And now we can go back to the one that you showed. So that the notebook. Why I did a digression is that in this case we create a single table with that is supposed to store Fibonacci numbers. And if you scroll down, we have some task that is computing the next Fibonacci number.
Mhm.
That simple compute data task, every time it runs, it will read data and it will write the next record from the previous records.
Mhm.
And this gets us to what I mentioned before, that we also track the writes. Now we can track this writing up to the row level. So if you scroll down to the chart, you can actually see the source or who wrote, what task generated, and the hash of the inputs and the outputs for every piece of data. So it's a bit an extreme example, but we can track up to row level anything that happened.
No, it's really cool though. You can see the compute hash is actually the same for each one of these steps, right? You're always just running the same Fibonacci code to go and compute the next number.
Yep.
And then it's just the outputs changing each time. And this output hash, is that just a hash of like the number 5 and the number 3?
It's actually the hash of the row.
The row in the table.
Yeah, the row in the table. A row in the table can have more information than just the actual number. But anyway, let's keep that for another time. So a row could also have integrity proofs from the writer. So assuming that you are not computing the Fibonacci number, but you are aggregating some positions from different sources, you could have signatures from the sources of those positions, and then you can generate a proof, or you can have a lineage for the aggregated or the sum of some numbers.
No, I love it. But it all comes back to the same theory, right? You want to go and have a proof of the input, a proof of the computation, a proof of the output, and then you want to have it signed. That's sort of like the core idea between pretty much everything in cryptography, right?
Or for lineage.
For lineage, yeah, exactly.
Yeah.
Well, maybe we could walk through the. Sorry, did you want to say something else?
Yeah, I wanted to say that we also do the same thing for APIs.
Exactly.
So all our API calls have lineage, and even more, we can run a Docker image. So any third party, any HTTP, HTTPS WebSocket service can be that can run as a Docker image. We can forward the request to that inner task and add this verifiability layer on top of it.
Yeah,
So,
I think you told me before that we can actually take any API task and give it almost any of these properties of data, right?
Yeah.
Including the tokenomics. You could go and charge for these API calls, right?
Yeah, exactly. So lineage and tokenomics can be added to any, basically zero changes on the on a REST API service, for example. You just run it as a Docker image, have a node that wraps it, and you have tokenomics and lineage.
I love that. You set up this ping example, sorry, this ping one as an example of this, right?
Yeah.
Or at least for the signed API.
Yeah. So in the network, you have to select the ping. And in the response headers, we add some extra hashes. Again, we have a hash of the input. The input is the request, the parameters that are sent, and also the headers that are passed the request. We have the output, which is the blob, the body of the output, and we have a signature. We also have a timestamp. The timestamp is a network timestamp if the node code is part of a sidechain, or if it's a individual node, it's the system time. And we also have the chained signature, the input-output signature, which is chaining the timestamp, the inputs, the outputs, and that's it. The node is known in this case. The result is that the node can vouch first for the output, that it comes from it, and then for the lineage, the full lineage, that a certain input generated a certain output from that node at the moment in time.
Super cool. And a quick shout out to Pat White over at Bitwave. We've been having a fun conversation with him about like verifiable API calls, where he pointed us in the direction of some other service that was doing these signatures and headers, and it was too good to pass up, and we thought it was a cool function to add over here. Well, look, this is a super deep dive into this concept of computational lineage, right? And sort of what's valuable over here. I'll see if I can go and add a few slides over here from our architecture documentation, in case anybody wants to go and follow up in the future. But let's say that the key ideas over here are that for that lineage, we are actually taking an audit table as well to show every read, write, and computation action that's done. And when we are establishing a computational lineage, we want to keep track of all input parameters, the data that's read, the computational task, the output, and then we want to go and sign these by the weave chain node that's actually doing it. But let's say that to close this out, let's go and tie this back to what's happening right now, especially with artificial intelligence. So one of the obviously ChatGPT and these other tools are really exciting because of their functional capacity. But these large language models have been trained on tons and tons of data, and it's not quite clear what specific data sets they were trained upon. So the EU has been debating some really comprehensive AI regulation. It's their EU AI Act, and it's going to go and establish some rules of operation for companies that are going to go and deploy these really powerful large language models. And one of the things that really jumped out at me from this article, which again was just released, I think, on last week, was that they are going to go and say that for these foundational models, the purveyors need to declare whether or not they're using copyrighted materials to train their AIs. And this is really important because, Barry Diller actually had a great point over here. These AIs are becoming like really, really effective writers and summarizers. And there's a decent chance that they have been trained on, professional publications that have just been made available to the open web without firewalls. And it's not just that they have done this maybe to date. First off, this is pure conjecture on my point. I don't have anything more than what I've been reading in these articles. But it seems very likely to me that, if I was developing a large language model, I would just go and have it suck up every piece of work that was available for free on the internet for my training model. And it will be doing so going forward as well. There was, some backlash even against Google a few years back when they were using their AMP product that made it so that, in your news site, you could go and say EU AI Act, and then go and get some blurbs over here that would, prevent me from having to open this link for Time Magazine, but still get the gist of the article kind of thing. AI is way worse, right? If you go and ask the AI what's going on with the EU AI Act, and it can return this information for you without me ever having to come to Time Magazine to go and read, from what they've paid their journalists to go and uncover, their whole business model becomes at risk. And, I think we chatted a little bit last time as well about some of the backlash against, even Adobe Firefly, where, let me see if, I don't know if I have this one available, but, artists had been pushing back against Adobe Firefly, saying that they were worried that it had been using their works to go and train off of without their acknowledgement. Adobe is making strong pushes to go and say, it wasn't stealing artists' work, and that it used stuff that was available for use. But it's a really big concern that, that how do you know that that's actually the case? And what we're trying to do at WeaveChain is actually make it so that if this type of computational lineage exists for the training of these AI models, that you as a user would be able to go and show that, your specific image had not been used in the training of Adobe Firefly, for example, or your specific article had not been used, in the generation of, in the training of ChatGPT. Now, this is likely going to have to be something that is done at a volitional level right now, because while, the EU AI Act is saying that, this needs to be declared for copyright material, there is no requirement for these purveyors to declare whether personal data has been used in the training of these models. And that's a really scary proposition. If we go back to the origin story of how we started doing lead chain with Mana, we wanted to go and respect user data properly and give users this data of how this information about how their data was being used, because we think it's the right thing to do. That is just not going to be the case for all parties in the near future. But we hope to be part of the change that goes and treats data like a first-class citizen. I think we could probably leave it there. Do you have any other comments on the AI training approach, Johnny?
No, I think there are two separate things there. One is the lineage, having a lineage for the AI model to be able to prove that the training happened on a certain data set. And then there is, I see it as a separate motion, and to be able to query that if your data was part of that data set or not.
Yeah, you're absolutely right. Like, these hashes could not be used by an individual to go and show if your data is in the set.
They can still be done. I mean, if you need to have a Merkle root hash, then you need access to the full Merkle tree that can be validated with a Merkle root. And then,
you would have to do something similar to Binance's proof of reserves thing, where every user has, the Merkle leaf for their data set, and then they can go and download the Merkle tree and validate that it rolls up to this Merkle root, right? I'll just wrap up over here with a last comment and say, actually, we're planning to go and explore a lot of these concepts a little bit further this summer. We're going to be at EthCC, so please shout out if you're interested in joining us. But we're going to go and potentially sponsor and likely participate in the Augment Hack hackathon, where we're going to be understanding the combination of Web3 and AI and exploring some of these concepts for notarizing authenticity and how to sort of charge these AI models that are training on user data. But I think we can leave it there for today. I'll go and strike this off of our list. Johnny, what do you think we should chat about next week?
I don't know, confidential compute.
Confidential computing? Oh, I do love confidential computing.
Maybe. I don't. Let's see if there's something more appealing than that. Yeah,
I think it's a good stopping point. So, how could you go and let's say train an AI model on remote data without ever giving exposure to the data itself, like we did in some of these models. But until then, thanks again, Johnny, and thanks for everybody for listening. And please shout out if you have any other topics that you want us to cover on the future of data.